Hello and welcome to the Postcard Professor, where we take complex ideas and explain them in the space of a postcard. In this video, we're going to be looking at both the ideal gas law and compressibility. What happens when we deviate from the ideal gas law? So ignore the chart on the right-hand side for a moment. We'll come to it later. For now, I want to look at specifically the ideal gas law. Now, if you've taken chemistry, you've probably seen the ideal gas law as PV is equal to nRT. And for this equation, P is the pressure, V is the volume, N is the number of moles, which is a count of the number of atoms, and then R is the universal gas constant, and finally T is the temperature, which is measured either in Rankine or Kelvin. It needs to be an absolute temperature. Now, for thermodynamics, we're going to change this just a little bit. First off, we don't like dealing in the universal gas constant if we can help it. It's necessary, but it's not our default setting, and so we're going to actually rename that as R bar. Second, we're going to divide through by the mass of whatever gas we're looking at. To start off, the volume divided by the mass is simply the specific volume, right? That's that lowercase v that we prefer to use in thermodynamics. I'm going to leave this N divided by M alone for just a second, and we can leave the R bar T alone as well. So the next simplification we're going to make is we're going to take this N, the number of moles divided by the mass, and recognize that that is 1 over the molar mass. So the molar mass, if you remember, is the mass that a certain number of atoms accompanies. So this is usually measured in grams per mole, or, as we prefer, kilograms per kilomole. So we have one more simplification step. We always know that the universal gas constant is 8.314 joules per mole Kelvin. But since we prefer dealing with kilograms, and we have kilomoles over here, we actually want to just put a kilo in front of both of these. And so we end up with kilojoules per kilomole Kelvin. Now, in order to actually get to the gas constant for specific gas, we have to divide by the molar mass. So this R bar divided by the molar mass is going to be the R of our gas, depending on what that molar mass is. So for instance, we can find the gas constant for air by taking that 8.314, this is kilojoules per kilomole Kelvin, and divide that by the molar mass of air, which is 28.97 kilograms per kilomole. So if we simplify this out, that we get that the gas constant of air is 0.287 kilojoules per kilogram Kelvin, which means that our final equation is going to be PV is equal to RT, where this R is now the gas constant, not the universal gas constant, but the gas constant for a specific gas. Now, I want to spend just a moment to look at the units of this equation. The specific volume we like referring to in meters cubed per kilogram. The temperature we're going to be dealing with in Kelvin, and we just said that the specific gas constant was in kilojoules per kilogram Kelvin. So if we go ahead and solve for our pressure, just in the unit sense, we can figure out what the units of pressure need to be in this equation. So we take our right-hand side, which has the kilojoules per kilogram Kelvin, multiplied by units of Kelvin, and then divided by units of specific volume. So this is going to be kilograms per meters cubed. And we can see that our kilograms will cancel out, our Kelvin will cancel out, and we're left with kilojoules per meters cubed. Well, we can simplify that just a little bit because we can say that our kilojoules is actually a kilonewton meter, and that's divided by meters cubed. And so that meter goes away and we're left with kilonewton per meter squared. Well, a Newton per meter squared is a Pascal, and so the units that we need for pressure are kilopascals, which is not typically the base unit of pressure. Oftentimes, whenever we're looking at tables, we have things in megapascals, and Pascal would be the base unit, so it's neither of those. It's very important that we use the kilopascals whenever we're using this equation. So let's run through a quick example. What we're going to do is we're going to find the specific volume of air at a temperature of 300 Kelvin and a pressure of 100 kilopascals. The reason I've chosen these values is that they approximate our standard atmospheric conditions. So if you walk outside, you're in the ballpark of 300 Kelvin, and you should be in the ballpark of 100 kilopascals. So plugging these in, we get 100 kilopascals multiplied by our unknown specific volume. That's going to be equal to this R of air that we found before. So this is 0.287 kilojoules per kilogram Kelvin multiplied by the 300 Kelvin that we have here. And if we multiply these out, we know that because we used the correct units, that the specific volume is going to end up being meters cubed per kilogram. And so our V here is going to be equal to 0.861 meters cubed per kilogram. So this is how we run through the ideal gas law. And again, if we know any two of these three values, we can figure out the third. Unfortunately, not all gases are ideal. So in certain circumstances, we start to deviate away from the ideal gas law. And that's exactly what this chart shows. If we can find this Z value, that tells us what the ratio PV over RT equals. So for an ideal gas, we know that PV is equal to RT, and so Z is equal to 1. So along this line, Z equal 1, that is the ideal gas line. Anywhere that we deviate from that, we're moving away from an ideal gas. In order to figure out what our Z value is, we need to know both our reduced pressure, which we're going to call P sub R, and this chart tells us that that is equal to P divided by P critical. And our T sub R is going to be exactly the same. It's the current temperature divided by the critical temperature. So if we know what the critical pressure and temperature are, so in other words, if we know what the critical point of a gas is, we can figure out what the reduced pressure and temperature are, and from there, we can figure out what our Z value is. Let's do this with an example. So let's say that we want to find the specific value of argon, the specific volume of argon, at a temperature of 225 Kelvin and a pressure of 10 megapascals. Gases tend to behave as an ideal gas at low pressures and relatively high temperatures. We're looking at a very high pressure and a relatively low temperature. So that means that we have a possibility of not behaving in an ideal fashion. Using this equation, let's solve for V. And we can see that this is equal to Z multiplied by RT over our pressure. And it turns out that that is equal to Z multiplied by the ideal gas law specific volume. So if this were perfectly ideal, then we would get a certain specific volume, but it's not, and so that Z is going to be multiplying it. Now, in order to find this, we need to know some information about argon. Specifically, we need to know the molar mass. For argon, the molar mass is going to be equal to 39.9, and that's in kilograms per kilomole. And we can find what the R of the ideal is by taking this 8.314 and dividing by 39.9. And that turns out to be 0.208. We multiply that by our temperature, which is 225 Kelvin, and then we divide by our pressure in kilopascals. And so this is in megapascals, so in order to get to kilo, we need to multiply by 1,000. The ideal gas law specific volume is going to be 0.00469 meters cubed per kilogram. Now, in order to find the Z value here, we need to know the critical temperature and pressure of argon. So the critical temperature of argon is 150.7 Kelvin. The critical pressure is 4.86 megapascals. Using these equations down here, we can find the reduced temperature and pressure. So our TR is equal to 225 Kelvin divided by 150.7 Kelvin, which is right at 1.4. So we know that our value is going to be on this line here. Our PR is going to be this 10 value divided by 4.86, and that's about 2. We can trace up from 2 and find where that intersects our point here. And that should be right in the 0.79 range. So we can say that Z is equal to 0.79 by using both the reduced temperature and the reduced pressure. And once we have that, we can say that our actual V is equal to 0.79 multiplied by this ideal V. And that value ends up being 0.00371 meters cubed per kilogram. So in short, the ideal gas law can give us good values for the properties of a gas under certain conditions, specifically low pressure and high temperature. So if we look over here, we see that as we go to a PR of 0, everything goes back to 1. And as we get to relatively high temperatures, that doesn't deviate as much even as we go to higher pressures. If we do have a relatively low temperature or relatively high pressure, then we can use the compressibility charts in order to get a good estimate of the gas's properties even in those situations. And so in order to do so, we need to find the reduced temperature and pressure, which we get from the critical temperature, critical pressure of the gas, and then use those two values in order to calculate this compressibility Z. And that Z is equal to the ratio of PV over RT. And so once we have Z, we can use that as a multiplier in our ideal gas law and get a good estimate of what our specific volume or whatever other property is. I hope you found this helpful, and I will catch you next time.